So, first things first. I'm sort of reluctant to pick problems or exercises for you to do. This is not for credit, right? This doesn't affect your grade directly. I don't want this to be a situation where I'm sort of like cracking a whip behind you to get you to learn, right? This is a 300 level class and everyone's expected to, at this point, have taken an active interest in their own education. So, when it comes to how will this affect your grade, it'll affect your grade on the upcoming exams because you'll be better on them if you practice. But there's no direct credit for it. So I don't know if I want to give you problems to work or just give you the general instruction that there are problems at the end of every section in the book, exercises at the end of every single section in the book. You can work these exercises, bring them to me on a piece of paper or take a picture of it and send it to me. And I will write comments. I will give you feedback on whether you're getting things right, whether you're getting things wrong, things that you need to focus on. Okay? Yes.
I was just, because I looked through it, because I realized that the stuff at the back of the sections would be really helpful. There are like at least 40 problems or something in the back of each section. So how will we parse through that many? Like, I'd love to go through them all, but I spent a 40-hour work week on senior design alone last week.
Mm-hmm.
So I definitely don't have the time to. How should we pick and choose?
Yeah, managing time is a big part of college life, right? What I would suggest is just go into the exercises, pick one at random from the first 5 and work it out. And if you find that it was very easy, didn't take a lot of effort, then maybe skip ahead 5 more and start working the harder ones, right? Just continue to push yourself up through these problems. Work as many as you can fit into the time that you have allotted for the work that you want to do for this class. And try to push yourself to sort of the edge of what is easy for you, right? Make sure you're working problems that take some time and that you aren't looking at them and just immediately knowing how to work them. So that's my biggest suggestion. Now, that's another reason why I wouldn't want to tell you which problems to work, is because that cutoff is going to be different for different people. And so,
and I guess this may be different for other people, I'd have to ask other people, but a lot of times, like, when I get to the homeworks or some of the problems I've tried to do out of the back of the sections, like reading through the chapter and even understanding it as best I can, when I go to those problems, I know nothing about how to do the problem. So it takes me at least like an hour of problem trying to piece through and puzzle together how it actually applies to a problem. So I feel like if I just pick problems, I'd struggle through each one and to try and I'd be looking at doing like at least to get through where I felt like I feel like I'd be spending several hours on each section, which I know I don't have time for.
well, a couple of things that I can say about that. The first thing is, I can't give you any way around that. Practicing problems is, I try to put my glasses on so I can see.
Might it be worthwhile to see if there are like other teachers who have assigned problems out of the book and try and do the problems they assign, since they might be tailored towards what might be in the test?
I'm not giving you problems tailored towards what's going to be on the test. The purpose of this class isn't to teach you how to solve certain problems, do certain types of things. Like the purpose of a calculus class is not to teach you how to get the derivative of a polynomial. It's to give you practice with learning abstract ideas and then applying them. And if I tell you how they're going to be applied, one, it's not going to be how they're applied in the real world, because this is a class where you're learning these things for the first time, so you're having to do them in a simplified situation. So it's not realistic. The other thing is, if I told you what kind of problems they were, you wouldn't be applying them to situations that you've never seen before. And that's really what you're in a class like this to learn, is to learn how to apply abstract ideas to situations in which you haven't seen them before. So, getting back to my answer to your previous question, these things do take time. There's really no way around that, and if it takes several hours, if that's what's necessary to learn the material and to learn how to apply it in situations that you haven't seen before, then that's simply the case. I think, hopefully, that's an estimate on the high end, that it will actually take less time than that. And then I think the other thing that you will find is that as you sort of exercise this skill, right, which is what we're here to do, you'll find that it takes less time. You get better at it, you get faster at it, and that's what we're trying to do. Right. So I hope that's at the same time, realistic, and I'm not trying to sugarcoat it, and I don't want to talk down to anyone. Everybody here is an adult, and you have to make your own decisions about how you spend your time, and what's important. But it isn't hopeless, right? There's a very simple answer to how to improve things, in the course of what we're doing in this class and what you would do in other math classes as well, and situations where you have to apply what you've done in math classes, and that is practice. And there's really no other way. And so we know what to do, and it's just a matter of doing it.
Yeah, I'm just trying to figure out, because if I had all the time in the world, I'd do all of it, but I'm trying to know how to best use my time since it's limited. But I guess I'll just have to work through this time and see how the next test goes. And talk to you again then if I'm still not figuring out how to find the right information. Because usually when teachers give us problems and stuff, that's what we see again on the test. And and it's okay that it's not like that. I just got to figure out how to work with something I'm not used to.
That's true. That's sort of in a nutshell what this is about: getting used to dealing with something that you're not used to. Yeah, I try to do things in this class in a way that you get some actual value out of this time you spend in it. In another class where you're given specific types of problems, know how to do a partial fraction decomposition, for example. Once you leave that class, you will in very high likelihood never perform another partial fraction decomposition. Or when you leave college, you will never do that again. But the skill of seeing that in a situation, knowing to apply partial fraction decomposition, for a strange example to choose, that's something that's useful and important outside of the narrow thing. There's always a pressure to make things easier, and I'm trying to evaluate how everyone's doing within the realm of what's possible. But I'm also trying to resist this, constant pressure to make things easier, to make things simple, so that anyone can do it. The purpose of coming here isn't because anyone can do it. It's because people who work hard and, you know, can do it. And we're attempting to reward people for working hard. Anyone else come in? That was a long philosophical monologue, basically, where I just talked for a long time. How does everyone feel about this? How does anyone feel about this?
And what do you mean, like in general, or?
In general,
I mean, well, I missed the part, I didn't know if did you give any kind of average for the test or average curve value that you're gonna put on? Like, I know there's still an outstanding test, but any ballpark values?
I can tell you that the average for the course was a 58%.
Okay.
So, you know, that's not the same thing as the median score, but about half of the people in the class got that score or lower.
Sure.
So, the curve will be quite a lot, and I don't want to say exactly how much, because for one, I don't know, and for the other, the grades that you're getting are not what's important. What's important is that you see that these are things that are, for example, row reduction. This is something that everyone, you'll see today in class, 35 minutes that we have left. We're going to use row reduction for that. We're going to use row reduction for everything. If you don't know how to do that, you're going to be, I'm not saying you, a student.
Yeah, a general you.
One will be completely lost when we come to the new material, and it doesn't sort of suddenly get easier, or we don't suddenly stop using all of the stuff that comes in exam 1. In calculus, things do branch off into various ways, and in linear algebra, it is more of a straight track. We are going along a progression of the same ideas, not the progression of different ideas. So, to not answer your question, which is how much is the curve going to be? It's going to be enough that most people pass, and the average will be around high C. Beyond that, I would really encourage everybody to focus on actually learning what's going on instead of worrying about how you're going to be evaluated at the end. Focus on understanding what we're doing and practicing and working through things. When you're in that state where you're struggling with a problem and you're not understanding how to do it, but you're maintaining focus on it, you're still working on it regardless of the fact that it's really uncomfortable to not know how to do something. That's when you're actually learning things, right? That's the state where you're actually learning things. And so focus on trying to get yourself to that point with this material. As often as you can handle as an uncomfortable experience, yes. And then trust that the evaluation will reflect that at the end. And then I realize that that's asking you to have a little faith in my what's the word I'm looking for? Compassion for you, my understanding and being fair. But yeah, just try to trust that if you really work at learning this material, your grade will reflect that. Anything else? I need to talk about determinants at some point today. Yeah. Sorry?
These are for SCP.
Yeah, so this is, I was split between either doing a curve, which is what I decided to do, and doing a sort of opportunity to redo the material on exam 1. So I kind of split the difference. I'm doing a curve, as you can see. This is a picture of it. And I'm also going to put some material, some extra, so all of the exams are going to be cumulative because I want to make sure that everybody recognizes and is rewarded for working on the earlier stuff in the semester because it's, you know, without it, the stuff later in the semester isn't gonna make any sense at all. What was I gonna say? It's a bonus question. I think I said this. It's gonna be a bonus question. You get some extra credit on your exam 1, but it's gonna be a challenging problem. It's gonna be a type of problem that wasn't on exam 1, but it will take the skills and require you to apply them, right? And it's strictly bonus, so if you don't wanna do it, you don't have to do it. It won't hurt your exam 2 grade at all, but, or your chances of passing the class or getting an A or whatever. Okay. But I am giving your exams back. That was the question. You asked me already. I'm losing the thread today. Yeah, they are for you to keep as long as you don't show them to any of the students who still have to take the exam. Hopefully it's for you to use to practice and to see what parts of the exam material. Okay, I'm gonna have to make an executive decision and cut off the exam discussion for now. We can come back to talking about specific problems on the exam as we work through them, but I want to talk about determinants today. The book has this nice sentence at the beginning of section 3.2. The secret of determinants lies in how they change when row operations are performed. And when I was preparing for today, I thought it said the magic of determinants. It's kind of, so this is properties. This isn't spelling class, hopefully I got it right. And so last time we talked about the process, how do we compute determinants? This is sidestepping the question of why do we even care what determinants are? Like, why do we care what the determinant of a matrix is? And I only really gave one reason, which was that if the determinant is 0, that means the matrix, the square matrix, because we only have a concept of determinants for square matrices. The determinant is, if the determinant is 0, then the square matrix is not invertible. It's a singular matrix. So that's the only real justification, but we'll see as time goes on that the magic of determinants is that they encode a lot of properties that we care about matrices. Invertibility is probably one of the most important properties that we care about. As we saw in the previous class, invertibility is equivalent to all of these this huge host of properties. So that's one thing that we care about, and so determinants will tell us if a matrix is invertible or not. So how do we compute it? We computed it by a process called Cofactor Expansion. And this was a process which was simple to explain, but computationally quite intensive. So let's do an example of this because we didn't have time last time. I'm going to write a matrix. I'm going to write entries of a matrix. And just looking at this, I feel like this is probably not a singular matrix. I just came up with it at random, so it's very likely that it's not a singular matrix. You kind of have to do a little work in order to get a singular matrix, or a non-invertible matrix. But we'll compute the determinant and try to figure out. So the cofactor expansion worked like this. We picked a row or column. And this was something that you saw in Calc 3 when you computed cross products. We'll go across this top row. That was sort of the default way that we saw it before. oh, let me change my symbols. Oftentimes when we're trying to compute the determinant of a matrix, we use this symbol around the entries, so a straight bar like an absolute value. You can think of the determinant as sort of a value that gets assigned to a matrix. So this absolute value symbol seems kind of appropriate. Okay, so now we're going to do cofactor expansion. We're going to pick a row or column, and we're going to, first of all, we'll choose this one, this row. That's sort of the default when they first teach you this. And we're going to compute sub-determinants. And then we're going to scale them by each of the entries here. So there's going to be an alternating sine rule, which you probably remember from Calc 3, plus, minus, plus. And the determinant will be first entry times the submatrix you get by wiping out the row and column that entry is in. So that'll be this submatrix right here. 9162. Now we move to the next entry in the row, that's a 2. And the sine rule, the alternating sine rule, tells us that that will be a negative. So -2. And then the submatrix that we get by wiping out the appropriate row or column, or covering them up. 4062. And then the alternating sine rule says that we do plus, the scaling factor is 3, and then the submatrix is 4051. Now we've gotten this expanded, cofactor expanded, and each of these determinants is now a 2 by 2, and we know how to compute these without a sort of cofactor expansion rule. Multiply these entries, and then multiply these entries, and then subtract this product from this product. So we did 1 times 10 minus 6, minus 2 times 8 minus 0, and then 3 times 4 minus 0. So this is 4 minus 16 plus 12. Oh geez, does that work out to be 0? Okay. Turns out we do have a singular matrix. Now, how can we show that? What's another way that we can show that? We could take these columns. This was an example that we had on the exam tape. Take these two columns and find a linear combination that's equal to this one. That would show that these columns are linearly dependent. One equivalence to being non-singular. We could do row reduction on this. And in fact, let's do row reduction and see what we get. We're gonna go to the point where we've eliminated these entries right here. So we'll make it an upper triangular matrix by row operations. We're gonna do row operations to eliminate this entry and then this entry. And we'll see what we get. We should get something that doesn't have a pivot in every row and column, right? If it had a pivot in every row and column, then it would be invertible. So what do we get? Go down this way. Top row stays the same. I'm going to eliminate this row. So subtract 4 times this, that's 0. Subtract 4 times this, that's 5 minus 8. Subtract 4 times this, that's negative 6. And then this one, the entries. We're talking about a matrix now, so I'll just use a matrix symbol. Now, I will use this entry to eliminate this entry. I'm not going to scale this, even though it would make it easier. So I'm trying to illustrate something. So we'll go here. This was accidental. This is totally accidental, I swear. I wasn't trying to come up with a single matrix here. Purely by accident. So now 1/3 of this is 1, and 1/3, or -1, and 1/3 of this is -2, and so we completely eliminate that bottom column as we were expecting. 0, -3, -6, 0, 0, 0. And now from looking at this, we see immediately that what we get is, well, this is a non-singular, or this is a singular matrix, it's non-invertible. Right? We have a pivot here, we have a pivot here, and then we have no third pivot, it's all zeros. Okay. So this was doing row reduction, just doing row operations, without scaling. The only thing we ever did was take a multiple of one row and add or subtract it from or to another row. Not the same row. We never did it to we never applied a row to itself. Okay. And now, let's look at the determinant of this thing. It's row equivalent to this one. And if they're row equivalent, they're either both invertible or they're both non-invertible, right? Because when we apply these row operations, we preserve the invertibility. So the determinant of this thing has to be 0. And let's attempt to do cofactor expansion on this one. Well, if we go across this top row, then we'll have 1 times this submatrix. Yes.
If you can do all those row operations, can't you just move the 0, 0, 0 to the top and easily see that it's 0?
I'll move the 0, 0, 0 to the top. That's fine. Ah, so I didn't use any transposition either, right, in this process.
Does that matter?
It's something that I will come back there.
So it does.
Well, let me, it does. It does matter. I'm trying to maintain suspense. So, if we went across this, let's say we did do things the same way as here. We would have 1 times the determinant of this submatrix. You can see that it'll be 0 minus 0, and it'll be 0. 2, of this submatrix, 0 and 0. 3, this submatrix, the determinant will be 0 minus 0 again. It will be 0. Now, to illustrate this process of cofactor expansion, I will decide to not use the top row. Like I said before, we can use any row or column. All we have to do is respect this alternating sign rule. And the alternating sign rule applies just as you might expect, going horizontally or vertically anywhere in the matrix. So going down from here, we get a negative and a positive. So it alternates positive, negative, positive, negative, positive, negative, positive, negative, positive. And so instead, I'm going to use this column here. I could use the bottom row as you suggested, but then I wouldn't be illustrating using a column. So I'm going to do that. So let's use this column here. We will have 1 times, if we eliminate this, and we eliminate this, then it's minus 3, minus 6, 0, 0. Going down 1, plus minus plus, alternating sign, so this is minus 0 times something. Doesn't matter what that something is, 0 times anything is 0. Alternating sign, 0 times something. I'm not saying these aren't good questions, right? It's a very insightful thing to notice that. But I also have to do some examples here. Something here is something here. It doesn't matter what these things are. This is 0 minus 0 plus 0. And that was a little easier to do, right? Because we picked a column that had more zeros in it. A column or row that had more zeros in it. Now, of course, in the end, we can just choose this column, or this row, and get 0 times some determinant. determinant minus 0. Let's see, this would be plus minus plus. So 0 minus 0 plus 0 equals 0. It's not immediately obvious from the rules that we use that no matter what row or column we decide to start with, we're always going to get the same determinant. But it is a fact. If you work out the formula, you work out the mathematics, I think you'll see the best things. I'm going to pause for just a second to see if you have any questions. Any more questions?
So, how do you determine, like, I guess, the orientation of it? For some reason, I just assumed you'd be like, you'd have like -3, -6, like, get put into a column, so maintaining the row.
I'm not sure what you mean.
What stops it from like just rotating those numbers when you choose to use a row for the cofactor expansion?
Or a column instead of a row.
Yeah.
So, that's an interesting question. It would take a little while to sort of work through the details of that. If we look at how the cofactor expansion works, it's a little bit of work, but not too hard to see that, you know, the same rule applies, and the rule that we're using isn't, you know, let's rotate this thing or transpose this thing. It's let's look at these particular submatrices. That's just the rule for computing it. We only have to convince ourselves that the rule works. Yes.
Maybe I missed it. You're multiplying all of them by 0. Is that just the determinant or just the bottom row of a reduced matrix or what?
In this
your
example right
yeah.
here.
Mhm.
So as we went down this column, the entries that we were multiplying the resulting submatrices by, or the sub-determinants by, were this entry, and then this entry. We made a clever or, you know, intelligent choice to choose a column that had more zeros in it.
Okay.
Right? Because we have a choice, because it doesn't matter which column or row we expand upon, we do the cofactor expansion through that row or through that column. When we did it through this first row, we would have had a multiple of 1, a multiple of 2, and a multiple of 3, right, being added and subtracted together. In that case, we would have had to compute each of these determinants. And we saw just by looking at it